All right, well, it is, let me see here. Okay, 10:39. Hey, got another minute. Um, well, welcome to the second day of World Water Week. My name's Daniel Carey Whalen. I'm the director of the Centennial Museum in Chihuahua Desert Gardens. We're one of the hosts of many hosts here at UTEP. And who's having fun so far? Can you see a show of hands? Okay, woo-hoo, all right. Yeah, really exciting. We got a lot of stuff going on today, um, and a lot going on tomorrow. We have the keynote speaker tomorrow, Kim DeWolf, who's a professor in philosophy from the University of North Texas. She'll be speaking at 12:30. Lots of stuff going on, so check your calendar. This group is water models and technology for decision making. We have four presentations, and they're all talking about different kinds of technology, detection technologies, simulating and predicting, using computational data analysis. So really kind of getting into kind of the data side of the water. And we have four presentations and not a lot of time, so I'm going to hand it straight off to our first presenter, Damian Gallegos.
Hi, thank you. Yeah, thank you. No, it doesn't work. Yeah, I can, I can do it from here. Good morning, everyone. My name is Damian Gallegos. I'm a PhD student. This is my first semester here at UTEP. Today, I will be presenting you a machine learning approach to support urban arid household landscaping. So the agenda for today is we're going to start with the motivation, background, challenges, related work, data and engineering, model tuning, results and evaluation, conclusions, and future work. I want you to introduce you to the problem. As we already know, here at El Paso, we have a lot of water scarcity, and the increasing demand is rising the cost of water. So for this, we need water conservation strategies, specifically aimed for residents. And just for you to know, between 40% and 70% of total water consumption occurring here in the Paso area, specifically for landscaping, it's between 40 and 70% of the total water consumption of a household. So we are trying to create tools that can support residents in making data-driven decisions that they can help them to have better water management strategies specifically for landscaping. So how can we how can we use machine learning into us so we can uh, predict reference evapotranspiration for urban landscaping, specifically for semi-arid regions. So this is going to be our approach. We're going to start first with irrigation schedules, then we're going to integrate botanical information, and a little bit of background. Evapotranspiration refers in broad terms about the water and energy exchange between the atmosphere and soil. You can see there the precipitation, transpiration, evaporation, all of these things together produce evapotranspiration. And for this, we have a lot of biophysical models. The most popular one is the Food and Agriculture Organization Payman-Montier, FAO-PM. This FAO-PM is used for reference evapotranspiration, ETO. And the problem with this biophysical model is that it only works for ideal conditions. These ideal conditions are for homogeneous vegetation, such as crops. But for this case, in this scenario, we are aiming to predict evapotranspiration for specific plants in urban areas. There you can see a small equation that is multiplying the reference evapotranspiration times the specific plant coefficient. So for the model data, we have 33 weather stations from Chihuahua with daily average of reference evapotranspiration with 15 minutes lapse between 1 and 5 years of data. We are using a training set of 26,000 data points and 6.5 Ks for testing. On the right side, you can see the features that we are using for training the model. Uh, those are the lapsed days, the mean temperature, the minimum temperature, the maximum temperature, wind speed, solar radiation, and relative humidity. For this presentation, we use 8 models, 4 deep learning models that are the MLP, GRU, LSTM, convolutional LSTM, and 4 machine learning models, linear regression, XGBR regressor, random forest, and support vector regressor. To the right side, you can see the metrics that we use. The deep learning models were tested using the following architecture. You can see that the MLP model has 4 layers with 26, 10, 2, and 1 units. And you can see epochs, batch size, learning size, and weight decay for all the models, the deep learning models. For the machine learning models, we know that the random forest regressor was the best performing algorithm, the best performing model, sorry, followed by the HGB regressor, support vector regressor, and linear regression. For the deep learning models, we have that the best model was the multi-layer perceptron model, followed by the convolutional STM, LCM, and GRU. Due to time constraints, we are going to focus on the best 2 performing algorithms. These 2 best performing algorithms, as you can see, on the right side, you can see that the MLP model tends to not predict too well around on values higher than 9 millimeters per day. And on the other hand, the random forest regressor model can predict very well all the seasonalities of the data. We performed SHAP analysis on these 2 models. And as you can see here, the solar radiation was the most important feature on both models, followed by the relative humidity, the maximum temperature, wind speed, Tmean, mean temperature, and minimum temperature, followed by the elapsed days. And we perform further SHAP analysis, and you can see here that the wind speed, the U, is having a lot of impact on the model. So what does it mean is that the wind speed, as higher that is the stronger the wind speed is, the most higher the positive impact you are going to have on the model. In this case, the reference evapotranspiration is going to increase, and in the same way on the solar radiation. We perform the same analysis on validation data. This is another weather station, separated from the dataset, and we have very similar results. But one thing about the MLP model is that around July and June, those are the 150 days, the model tends to underestimate the values of the evapotranspiration. And you can see that the actual values, reference evapotranspiration values are the blue dots, and the predicted values are the orange dots. The same here for the random forest regressor, but as you can see here, the random forest regressor model tends to predict better than the MLP model, specifically around the 150 days. So After we have our models, we are going to test this with botanical data. In this case, we're going to use the sunflower. And the sunflower has 120 days of growth. And those stages are 4 stages of growth. And they go around June to September. And these 4 months, it's actually June, July, September, and October, 4 months. Okay. So once we have this data about the sunflower, you know that every single species has a specific coefficient. This coefficient is going to vary between all the stages. And if you apply that using the equation, and you're going to have how much water that specific plant is losing on those specific, in each specific stages. You can see here that the random forest regressor model is performing very good precision predictions for for reference evapotranspiration. Those predictions tend to be a little tend to have a little bit of overfitting around the 60 and 80 days. These specific days are around July. That's because we have a lot of temperature. And on the other case, the multi-layer perceptor model tends to underfit or underestimate the evapotranspiration values. So as conclusion, the random forest regressor and the MLP models are very similar. Each model learn different characteristics of the data. One of the models can underestimate and the other one can overestimate around the July, June months. Those are very important months because we have a lot of temperature here at El Paso. And we know that the solar radiation has the most or the greatest impact on the model. And also wind speed merge has a more significant factor at higher speeds. And we know that both models perform very similar on validation data. For future work, we want to integrate more data because we have limited data for those 33 stations. And if we want our model to be better, we need more data. And also we want to include other features such as microclimates, droughts, precipitation, and of course, add additional urban areas, so different to El Paso. And obviously we want the involvement of stakeholders, and the exploration with more plants or vegetation data. These are all acknowledgements. I don't know if you have any questions. Why? Yeah, I understand the question. All these models have been tested on other areas with different data in different regions, similar to El Paso. And all these models have demonstrated that they are very good at predicting reference evapotranspiration. And the main thing about random forest regressor and multi-layer perceptron models, one of them is a machine learning model, and the other one is a deep learning model. Machine learning models usually right now are very good. They're very, very good at predicting data. And by that, usually machine learning models tend to overfit data. And even though the random forest regressor model works very well on this data, myself, I will choose the multi-layer perceptor model because all the parameterization is based on this specific data. It's a more personal model for this data, the multi-layer perceptor model. And we can also go into, for example, using hybrid models. And for example, the random forest regressor works very good at low temperatures. So, at high temperatures. So we can use the random forest regressor only for the months of June, July, August, and use the multi-layer perceptor model for the other months that are a little bit more cold. Yes.
Forgive my primitive question here. When you say machine learning, I'm taking that's not an analytical model. It's based on what, things like genetic algorithms or neural net type structures. The data is fed into it. It figures out how to match that data to the training data. It's kind of a black box as opposed to a set of equations. That's correct. Is that the correct statement? Would that characterize?
I think the general idea about machine learning models in general is that most of them are seen as a black box that can do pretty well, but we don't know how they work. And what to think about them is that, for example, the random forest regressor is you can think of it as more of a statistical tool than something that is more than like a black box, you know? For example, the random forest regressor uses statistical analysis and several populations. And by using several populations, we learn the best of the best features of each one. And then we merge. So it's more of a statistical tool than something that really has something that we know how.
What kind of a training data set do you need to come up with a basic robust model? I mean, how many data points? Can you do it with 100, 1,000? You need 10,000? How does that work for you?
Usually the more data that you have, the better the models. But you don't have, for example, we can have 1 million data points from El Paso region. But if we train a model on El Paso region, the model is going to overfit on the same data because it's very similar to that. So we need different data from different points of view, so our model can learn more things about different things, and it will be more robust. Yes. Mm-hmm. Yeah. Yeah.
Thank you very much.